October, November 2024. Paper 2, very much. Question 1, Part A. The shorthand electronic configuration of Cobalt is argon 3d7 4s2. Part 1. Identify what is means by the argon with square bracket by giving its full electronic configuration. First, we can use the periodic table to get the electronic configuration for any elements. So I teach you how to use it. Okay, let's say now we have this periodic table. So remember, the first row is n equal to 1. The second is n equal to 2, means n equal to 1 is the first shell, n equal to 2 is second shell, n equal to 3 is the third shell. And this is the fourth row is n equal to 4, fourth shell. Okay, so in the first electron shell, we know that is only s subshell and one s orbital. So therefore, the hydrogen is electron configuration is 1s1, and the helium is 1s2. Okay, after the 1s2, then it will fill up to the next row or next electron shell. So this one, the first two groups is under this S block, and from 3 to 12 is the D block, and from 13 to 18 is the P block. So means lithium, which is after helium, is 1s2 and 1s2 and 2s1. Beryllium is 1s2, 2s2. Boron is 1s2, 2s2, 2p1. Okay, so it's the first element in this p block. Okay, so if follow this this way, so we know that the argon is actually 1s2, 2s2, 2p6, 3s2, and 3p6, because this one is 3s and this is 3p. So the argon is the last elements in this n equal to 3, so therefore it's 3p6. So means the full electron configuration. So we know that. Okay, so just follow the so just follow this electron configuration. So we get this 1s2, 2s2, 2p6, 3s2, 3p6. So this is how we get the electronic configuration from the periodic table. So we can use the rows, okay, and the blocks inside the periodic table. Okay, so hope you understand. For part 2, the lowest energy electron in the cobalt is in the 1s orbital. Draw the shape of 1s. Actually, you just need to draw a circle. So it's better to show this axis x, y, z. So with a circle, this is 1s. As long as s orbital is spherical, so you just draw a circle. For this part 3 now, deduce the numbers of unpaired electrons in cobalt atom. The cobalt atom its electron configuration is given in the question, which is argon 3d 7 4s2. For s2, this s orbital already fully filled. Okay, 2 electrons there. In the d orbital, we know that the 3d orbital, okay, there are 5 orbitals, and only 7 electrons here. So the electrons will fill up this way. Fill singly first, then is pair out. Okay, so 1, 2, 3, 4, 5, 6, 7. So because now with this 3d7 configuration, so we know that it's actually still have 3 unpaired electron there. So this is how to get this unpaired electron. Okay, so the there are 2 pairs of electron and 3 unpaired electrons in the 3D. So this is the unpaired electrons mean. Okay, part B. Table 1.1 gives some details of the stable naturally occurring isotopes of rhodium and iridium. So we have this table we need to fill up. The proton number is very easy. You just need to read from this isotope. So the lower left here, this is a proton number, so you just fill up here. Okay, here is 77, and this one, same elements, these two, they are isotopes, so proton number is 77. For neutron, is quite easy to get it, so we just use the nucleon number, the mass number, minus the proton. Okay, so for this one, we use 191 minus 77, so we get 114. And for this one, we use 193 minus 77, we get 116. Okay, so now this is the part maybe is quite difficult for some of you. Total number of electron shells. So what are the total numbers of electron shell? So let's get back to the this periodic table. So we need to find this rhodium. So the rhodium is right here. Okay, so it's in the D block. So rhodium is actually in n equal to 5, you see, here. So that's why the total numbers of electron shell is 5. So we can get from the periodic table. So its electron configuration is 5s2, 4d7. So this is the numbers of electron shell for the rhodium. Next question, part C. Table 1.2 shows the relative abundance of isotope in the sample of alloy containing rhodium and iridium. So part 1, define relative isotopic mass. Isotope is the one that same proton number, different nucleon number, or the mass number. So because now it's asking isotopic mass only, so we must have this definition. The mass of a particular isotope. Okay, for example, like this iridium 191 and this iridium 193. So they are the particular isotope with certain mass number. So the mass of a particular isotope of an element, element is let's say iridium, so they are the same elements because different mass or different neutron number, so they are different isotopes of an element compared to the mass of unified atomic mass unit. Okay, so for the part 2, use table 1.2 to calculate the relative atomic mass for this iridium. So we just need to use these two isotopes, 191 and 193. So from this table, the relative abundance for these two in the alloy is given. So total relative abundance of these two is 50. 50. So what we need to use is the mass and the relative abundance, okay, for the calculation. So the calculation is this. So we use the mass, okay, times the relative abundance, okay, and this is another isotope mass times the relative abundance. So we sum it up over 50, so not over 100, because the total abundance of these two isotopes, 191 and 193 iridium, is only 50. So after that you get 192.35. Okay, part D. Hydrated rhodium chloride, okay, catalyze the conversion of ethene to but2-ene. Okay, both stereoisomers of but2-ene are formed in this reaction. Okay, we discuss later. Before that, so we have this calculation. Hydrated rhodium-3 chloride contains 20.5% by mass of water of crystallization. Deduce the integer value of the X, okay, in this sort. Okay, so very easy, because it's asking the water of crystallization. So what is this number? So you need to use a percentage together with the ratio. So because we don't know what is the X value, so we put the X H2O, right? Means the mass will be 18X over the mass of the salt. Okay, so the this rhodium-3 chloride, so is 209.4, okay, plus 18X. So when you get this ratio correct and using the percentage, okay, rearrange, you should get X equal to 3. So this is a standard calculations for this to get the water of crystallization. Of course, you can use another ratio that in the mark scheme, but normally we will follow this. This is a standard calculation. For this part 2 now, define stereoisomers. Stereoisomers, we have two types. One is the geometric isomers, and another one is the optical isomer. So now it's asking stereoisomer, means it could be both. So we need to use the different arrangement of atom in space to define this. Okay, so what is this stereoisomer means? Okay, they are the molecules with the same molecular formula and structural formula. Molecular formula everyone's know. Structural formulas, for example, for this but2-in, the formula is actually, the structural formulas is CH3 CH double bond CH CH3. With this structural formula, we don't know where the groups are being arranged, whether the larger group, okay, at the same site or different site, we don't know. So that's why when those molecules with the same molecular formula and structural formula, we still not really know where they're oriented or where is the arrangement of atom in space. So that's why, let's say I use a cis and trans to explain. Okay, the but2-in, it can be a cis isomer or it can form a trans isomer. So when the but2-in is having this structural formula, okay, so means the groups can arrange in this way. The CH3, which is the larger group, it can be at the same site. And the CH3, if now at different site, so this is a trans isomer. So that's why we say that the molecules, they're having the same molecular formula and structural formula. This is a structural formula, and it must be different arrangement of atom in space. When the atoms, they arrange in different direction, or like this cis and trans, so we know that they are stereoisomers. Okay, of course there are another stereoisomers, optical, right? That one is involved mirror images. So this is how you define the stereoisomers. It must be, their difference now is the arrangement of atom in space, whether it's the same site or it's different site. That's the arrangement of atom in space. Part 3. Explain how conversion of ethene to but2-in can be described as an addition reaction. Okay, so this one is quite straightforward. So it's already mentioned, this ethene now is formed but2-in. So because now it's the 2 carbon compound to 4 carbon compound, and from this C2 CH2, CH2. Now it's formed this butane. So it's actually involved two molecules of this ethene to form one molecules of butane. Is actually two form one. So two ethene added together to form one butane. So therefore, you just need to explain like this, because two ethene molecules now produce a single product, which is the but2ene. So that's why we call addition. The two ethene added up and form but2ene. Part 4. Draw the two stereoisomers of but2ene. Like I told you just now, the stereoisomers of but2ene, it could be trans but2ene or the cis but2ene. When the larger group, which is the methyl group, this one, they are at a different site. So this is trans isomer. When this methyl group, they are at the same site. So they are they are cis isomer. So it's cis but2ene, like this. If you want to draw a skeleton, you can draw like this, right? So this is CH3, CH, CH, CH3. Okay, this one same, CH3, CH, CH, CH3. Okay, that's all. Thank you.